Hello everyone, this is the second part of the tutorial where we will talk about data quality metrics for unstructured text data. In this part of the tutorial, we will briefly go over the motivation for addressing the data quality issues for unstructured text. We will first understand what we mean by unstructured text data and the different properties of text data with which we can assess its quality. Further, we will cover some of the prior art approaches proposed in literature to address different aspects of text data quality and then briefly look at some of the future directions for this domain. So, what is unstructured text? Unstructured text data comprises of free-form text as seen in emails, essays, letters, etc., or text extracted from formatted or semi-structured data such as documents, social media posts, tweets, product reviews, web pages, etc. Such text content, although having important information cues useful to any business, typically lacks structure and cannot be readily consumed by most of the AI models. To address this, in the recent years, a lot of work has been done in unstructured text mining. Standard methods of automatic document content extraction and indexing, natural language processing tasks such as named entity recognition, sentiment analysis, text classification, etc., have been widely adopted in the industry to leverage the unstructured text. However, with the growing amount of unstructured text being collected by organizations today, it becomes imperative to assess its quality to enable meaningful text mining tasks as well as useful AI models. There are a lot of standard pre-processing steps and best practices that have been developed to process unstructured text, such as removing HTML tags, irrelevant spatial characters, stop words, performing tokenization, lemmatization, stemming, etc. Although these steps are generally applied to text to reduce noise and construct good features for the AI model, they do not provide any insight into the quality issues of the data and if we can do anything about it. So, how exactly can we assess the quality of text? There are many different properties associated with the text data, and we can probe into these different properties to capture the quality of the text data. We can assess the lexical properties of the text data, such as the vocabulary size and diversity, the misspellings, etc. We can assess syntactic properties of the text, such as the POS tags, the grammatical relationship between different parts of the text, identify syntax violations, etc. We can also assess semantic properties such as ambiguous words, phrases, if the text is meaningful or not, or contains complex words, phrases, etc. Further, we can also assess the discourse properties such as readability of the text, text coherence, etc. And finally, we can assess the distributional properties of the text embeddings to study the outliers and topics, etc. We can group the different approaches for assessing text quality across these properties into two broad categories: approaches that assess the generic text quality and approaches that measure text quality with respect to a task. We discussed some of the generic text quality approaches in the previous slide, such as text readability, text complexity, lexical diversity, text cleanliness, etc., that measure the corresponding desired property of the text. To add to the list, we have text appropriateness, which measures the presence of offensive, inappropriate, or profane language; text formality, which captures the use of formal language in text; text bias, which detects the presence of biased language in text; and few other text quality approaches. For task specific approaches, the idea is to measure the quality of the dataset using the text samples and their associated labels, and further recommend the mitigation action to improve the performance of the task. For text classification, properties such as data diversity, imbalance, difficulty, etc., would help to address the gaps and prepare the dataset accordingly before implementing the ML pipeline. For addressing class imbalance in the dataset, assessing the quality of samples generated by different natural language generation approaches and filtering them would improve the dataset quality. Similarly, identifying interesting text pairs for semantic similarity dataset or interesting responses for dialog dataset or label noise in dataset would help transform it and make it suitable for the downstream ML task. We will cover the different approaches proposed in prior art for measuring these different type of text data quality. We will now first go over some of the generate text data quality approaches in prior art. The first paper is titled Automatic Text Scoring Using Neural Networks by Alikanitis et al. In this paper, the authors provide an approach to automatically generate a score for the input text given a standard marking scale. The novelty proposition is to learn word embeddings that capture both context and word specific scores. They train an LSTM network using these score specific word embeddings to generate an output text quality score. Finally, the authors showcase the efficacy of their model for predicting essay scores written by students ranging from grade 7 to grade 10. For the proposed score-specific word embeddings, the objective is to learn both the context and the word-specific scores for the embeddings. For learning context, they consider a sequence of words S equal to W1, W2, WP up to Wn and construct the corresponding noisy set S prime by only replacing the center token WT with a random token WC from the vocabulary V. The model then learns word embeddings by ranking the activation of the true sequence S higher than the activation of its noisy counterpart S prime through a hinge march loss, thus emphasizing the local context of the center word in the true sequences. To capture the word-specific scores, the authors simply apply a linear regression on the sequence embedding to predict the SA score by training the model to minimize the mean squared error between the predicted y hat and the actual SA score y. Words such as is, are, to, at, which appear with any essay score, are considered to be underinformative in the sense that they will activate equally both on high and low scoring essays. Informative words, on the other hand, are the ones which would have an impact on the essay score. Example, spelling mistakes. The authors argue for the advantage of score specific word embeddings over the standard embeddings through this figure. Since standard embeddings only capture the context of the word, incorrect spellings such as computer and laptop are placed close to their correct counterparts in the embedding space. However, score-specific embeddings discriminate between spelling mistakes based on low and high essay scores during training, and hence are able to separate the words in the embedding space while preserving the contextual information. Thus, in the figure you can see the correctly and incorrectly spelled words are separated yet close to each other as they are contextually similar. The authors further train a bi-LSTM model with score-specific word embeddings, and the LSTM sequence embeddings are fed to a linear unit in the output layer to predict the essay score. They compare their performance against different baselines such as doc2vec, word2vec, etc. on standard essay scoring dataset from Kaggle. Now the question that remains to be answered is how to capture the quality of text. Which words in the input text actually correspond to a low or a high score? The authors define quality as the level to which a word appearing in a particular context would prove to be problematic for the network's prediction. In order to identify the high and low quality vectors, they do a single pass of the input text and capture the LSTM model prediction, and instead of using the ground truth essay score, they consider a pseudo high score and a pseudo low score to measure the gradient magnitudes corresponding to each word. The intuition here is for a pseudo high score, if the word vector is of high quality, that is associated with high scoring text, then there is going to be little adjustment to the weights in order to predict the highest score possible and vice versa. In order to provide the insights for different low and high scoring words, the authors visualize the gradients for them as shown in the figure here. We can observe that positive feedback is given for correctly placing punctuation or long distance dependencies. For example, in sentence 6, whether they are and researching are related and both contribute highly to the score. On the other hand, negative feedback is given for POS mistakes and spelling mistakes. For example, in sentence 2, being patient contributes to the low score. Finally, there are mistakes that are observed to be made by the model. For example, in sentence 3 here, reader satisfied is given incorrect negative feedback. In this way, the authors have introduced a simple framework for learning score-specific word embeddings and providing a mechanism to expose the network's internal scoring criteria as a quality measure to assess the input text. The next paper that we have for generic text quality approaches is titled Transparent Text Quality Assessment with Convolutional Neural Networks by Osling et al. In this paper, the objective is to automatically assign a score to inputs to each text. Unlike the previous paper, they do not depend on a standard marking scale. The approach they take is to train a convolutional neural network model on character embeddings. The way they got around the need for a standard marking scale is to train the model by employing a pseudo-probabilistic framework to incorporate intuitive axioms on various quality text and high-quality text. They showcase their results for the task of essay scoring and predict against human graders and qualitatively analyze to identify low versus high scoring regions in the input text. For training the CNN model, given a sequence of characters s equal to s1, s2 up to sn, the authors propose to first construct a character embedding matrix V cross D, where V is the character vocabulary and D is the embedding dimension. The model employs one-dimensional convolutions with kernels of size 3, 5, 7, and 9 in order to capture character engrams of varying size and utilize residual connections for training. The final quality score is computed as the dot product of the output weight vector and the mean value of the outputs at the final residual layer. This structure implies that the model score for a text is the mean score over each symbol, which means that the score for any subsequence of a text can be computed without depending on the length of the sequence. For loss optimization, the authors propose a pseudo-probabilistic framework where probability of text A better than text B is given by sigma of QA minus QB, where sigma of x is the logistic function and Qx is the network score. In this case, better is used from the perspective of formal written Swedish, and poor text could either be informal or due to lack of competence. During training, the authors use the cross-entropy loss with the axioms as shown in the figure. P of A greater than B equal to 0 if A is a user-generated text, for example blogs, and B is a professional prose, for example news. P of A greater than B equal to 0.5 if both A and B are professional prose. P of A greater than A prime equal to 0.5 if A prime is a pair of block texts from the same author. And finally, P of A greater than B equal to sigma times Q of A prime minus Q of B prime if A prime and BB prime are pairs of block texts such as A prime is from one author and BB prime is from another. In simple words, these axioms mean all authors, professional or not, are consistent. Professional authors are better than blog authors. All professional authors are equal and blog authors are not equal. In order to provide the insights for different low and high scoring regions in the input text, the authors visualize the gradients for them as shown in the figure here, using the same approach as discussed in the previous paper. Here, red encodes low scores, blue encodes high scores, and faded colors are used for scores near zero. As observed from the samples here, news examples are scored higher than the blog examples. Informal spellings and use of smileys lead to low scores in the block text, which is evident from the red regions in the block text. In this way, the authors have introduced a simple framework for estimating the local as well as global quality of input text in a self-supervised fashion by employing a pseudo-probabilistic framework to incorporate intuitive axioms. Next, we will cover some of the approaches for outlier detection in text. Outlier detection and removal is an important pre-processing step prior to building a machine learning model. Usually, outliers are those points in the data which do not follow the general trends and stand out when compared to other points. Such points, if not removed from the dataset, might hamper the ability of a machine learning model to capture the data properties in a generalized way. It is relatively easy to understand the concept of outliers in the case of tabular or time series data. For example, by simply plotting a given tabular data as shown in figure 1, one can observe that one point lies away from the general trend and can be treated as an outlier. Or one can also find outliers by plotting statistical nature of the data such as using box plots in Figure 2, and identify points lying far away from the usual data distribution. Even in case of time series data, a simple plotting as shown in Figure 3 can help one discover outliers present in the data. However, it's not the similar case for text data. Given a text classification data, it is not clear what an outlier can be or how to identify it. There are multiple ways to interpret an outlier in text data. Given a data set, can the outlier be a data point which is topically diverse from data points? Or is it some gibberish text or some incomplete sentence which does not convey any meaning or data points having some foreign language when compared to majority? Here are a few examples from the popular IMDb sentiment analysis dataset. This dataset has movie reviews scraped from IMDb and labels associated to each review to indicate if the review is positive or negative. A data sample can be anomalous due to various reasons such as there is a lot of repetitive content in it, as shown in the first example. The sample is difficult to comprehend even for a human and assign a label, as shown in the second example. The sample is incomplete, as shown in the third example. From these examples, it can be observed that, leave alone the model, it might sometimes even be difficult for a human to understand and provide a label to it. Approaches for outlier detection in text can be broadly classified into two groups, the classical techniques and the deep learning based techniques. Now that we have seen some examples of outliers in text, let's discuss two approaches for anomaly detection in text. Outlier detection for text data was published in SIAM 2017 by Kannan et al. And proposes a matrix factorization technique to detect outliers in text data. Matrix factorization technique is predominantly used in recommender systems to decompose an interaction matrix into two low-dimensional matrices. The same technique is applied here to identify outliers in the given text data. Firstly, a numeric representation of the data is required, and a simple way of representing the document can be in the form of words present in them, which is a standard bag of words approach. Given a set of documents, the authors represent them as a term matrix A, m cross n, where m is the number of unique words in the given set of documents and n is the number of given documents. The term matrix A is decomposed into a low rank matrix L and an outlier matrix Z. The low rank matrix L is represented as a product of two matrices W and H. Intuitively, this corresponds to the case that every document A of I is represented as the linear combination of the R topics. In cases where this is not true, the document is an outlier, and those unrepresentable sections of the matrix are captured by the non-zero entries in the outlier matrix Z. Each entry in the Z matrix corresponds to a term in a document. The aggregate outlier behavior of the document X is computed as the L2 norm of the column Z of X. For testing the results of the proposed approach, the authors consider standard datasets and sample outliers from a unique class while preserving the other classes as regular classes. The results are analyzed using the receiver operating characteristics (ROC) to evaluate a ranking of outlier scores by examining the trade-off between the true positives and the false positives, as the threshold on the outlier score is varied in a range. The approach is also able to detect outlier documents from regular classes. Patterns such as unusually short long documents, unique words, vocabulary repetition, etc. are observed in detected outliers. Thus, this paper covers an outlier detection framework for text documents that capture the underlying semantic topics in the corpus and accordingly identifies the outliers. The next paper on unsupervised anomaly detection in text was published by Ruff et al. Unlike the previous approach, this paper relies on recent techniques such as pre-trained word embeddings and deep learning architectures to identify outliers present in the data. The authors propose a one-class classification method which takes an input, the word embedding, and identify if the input text is an anomaly. Similar to the previous technique, the first step here is to represent text in a numerical format using pre-trained word embeddings. For each word in a sentence, Embeddings are obtained, and the next task is to represent all the sentences in a fixed size representation, irrespective of the number of words in it. Here, the authors utilize a technique called multi-head self-attention, which maps variable length sequences to a fixed length representation, and additionally gives multiple numeric representation for the same sentence considering multiple contexts. For example, the word March can be a month or a march past. Hence, based on the context, a different representation is required for a given sentence. In the self-attention, given a word embedding matrix of the input sentence, the attention matrix is computed as shown in equation 1. Once the attention matrix is computed, it is multiplied with the word embedding matrix to get the sentence representation as shown in equation 2. Once the sentence level embeddings are obtained, the authors propose a way to determine the context vectors. These context vectors are expected to behave similarly as the sentence representation, with an additional constraint that different context vectors for the same sentence capture diverse contexts. The context vectors are determined using equation 1, which minimizes the cosine distance between the sentence embeddings n and the context vectors c. As mentioned, the orthogonality constraint is imposed on the context vectors to capture diverse contexts. Once the loss is minimized, most of the context vectors have similar representation to that of the sentence embedding matrix n, and some do not. We can quantify the similarity between these two representations using a cosine distance function. For a given context, cosine distance is computed with respective representations of sentence and the context vectors. Now, in order to get a single score, the scores for all the contexts need to be aggregated. They can either be given the same weights and averaged as shown in the equation 2, or can be assigned different weights and a weighted average can be taken. Higher the score S of h for a given sentence, greater the chance it is an outlier, since its context vector is away from the sentence embedding. The authors report the performance of their framework on three standard text datasets by employing a one-class classification setup and show improvement over the baselines utilizing different standard word embeddings. In this way, the paper proposes an unsupervised approach for anomaly detection in text by utilizing context vectors. Further, there are many more approaches in prior art that capture the different text data properties we observed earlier and propose novel methods to assess the text data quality. Metzger et al. Propose a local coherence model that captures the flow of what semantically connects adjacent sentences in a text using an LSTM-based deep neural network. Jain et al. Propose an unsupervised approach for controllable natural language formalization. Requesens et al. Propose a systematic framework to identify the bias-inducing words or phrases in a biased text. We will now look at some of the task-specific text quality approaches, and we will start with a few for text corpus filtering. The first paper is titled Aiming Beyond the Obvious, Identifying Non-Obvious Cases in Semantic Similarity Datasets by Peneld et al. In this paper, the objective is to identify the obvious and the non-obvious text pairs for semantic similarity datasets, which are part of a SEMVAL, a series of international natural language processing research workshops whose mission is to advance the current state of the art in semantic analysis. The approach the authors take is to compare the Jensen-Shannon divergence (JSD) of the text snippets against the median JSD of the entire distribution, and categorize the text pairs having low versus high divergence. The task they evaluate their approach on is the SEMVAL community question answering, where the objective is to rank relevant posts above irrelevant ones, given a text query. Some examples of obvious and non-obvious pairs are shown in the first figure. An obvious semantically positive text pair is "What's the origin of the word o'clock?" and "What is the origin of the word o'clock?" On the other hand, a non-obvious semantically positive text pair is "Which is the best way to learn coding?" and "How do you learn to program?" Similarly, an obvious semantically negative text pair is "What are the range of careers in biotechnology in Indonesia?" and "How do you tenderize beef stew meat?" A non-obvious semantically negative text pair is what is meant by E in mathematics and what is meant by mathematics. The authors select well-known benchmark datasets differing in size, document length, document types, and tasks, and they plot the lexical divergence distribution. To characterize the datasets, the text pairs are represented as two distribution over words. Their lexical divergence is measured using GST as shown in the figure. The datasets differ with respect to the degree of lexical divergence they contain. Pairs with negative labels tend to have higher GST than pairs with positive labels. Semantically positive text pairs having high divergence and semantically negative text pairs having low divergence are both categorized as non-obvious samples. These are generally regarded as difficult samples for the models to predict on, and hence the proposition is to improve the model performance on these text samples. Thus, in this paper, the authors propose a simple and effective way to identify the obvious and non-obvious text pairs from semantic similarity text datasets. The next paper is titled Improving Neural Conversational Models with Entropy-Based Data Filtering by Zaki et al. The objective here is to filter generic utterances from dialogue datasets to improve the model performance. The authors devise a data filtering approach by identifying open-ended inputs which are determined by calculating the entropy of the distribution over the target utterances. Here, the task is to measure custom metric scores such as response length, KL divergence, coherence, blue score, etc. for standard dialog datasets based on source or target or both mechanisms to evaluate the model performance. The generic utterances can occur by considering the entropy of the source with respect to target distribution and vice versa. For example, a source utterance such as "What did you do today?" has a high target entropy since it is paired with many different valid responses in the data. On the contrary, a source utterance such as "What color is the sky?" has a low target entropy since it is observed with few valid responses in the data. Similarly, a target utterance such as "I don't know" has a high source entropy since it is paired with many different inputs in the data. On the other hand, a target utterance such as "try not to take on more than you can handle" has a low source entropy since it is paired with few valid inputs in the data. The authors perform several experiments to showcase the importance in the model performance on the list of custom metrics by filtering the generic utterances based on the calculated entropy. In this way, the authors showcase a simple approach to identify the presence of generic utterance in dialog datasets and provide a measure of the dataset quality. Now that we have seen various quality metrics for quantifying quality of given text data, how do we know what is the right combination of metrics to understand the complexity of a dataset for a classification task? The next paper attempts to solve this exact problem. The paper is titled Understanding the Difficulty of Text Classification Tasks by Collins et al. This paper proposes an approach to design data quality metrics which explains the complexity of the given dataset for classification tasks by considering various properties of the dataset such as class diversity, class imbalance, class interference, and data complexity. Class diversity characteristic is used to get the count-based probability distribution of classes in the dataset, such as Shannon class diversity and Shannon class equitability. These metrics consider the class distribution and measure diversity of the dataset. Class imbalance characteristic is used to measure the amount of imbalance present in the data and is computed using the formula shown where C is the total number of classes, NC is the count of items in class C, and T data is the total number of data points. Class interference characteristic is used to measure similarity among samples belonging to different classes. The authors consider Hellinger's similarity, which measures similarity between two probability distributions. Top n-gram interference, which is the average Jaccard similarity between the set of the top 10 most frequent n-grams from each class, and average mutual information score between the set of the top 10 most frequent n-grams from each class. Data complexity characteristic is used to measure complexity of the data based on linguistic properties. The authors consider Distinct n-gram, which is the total n-gram minus the count of the distinct n-grams in a dataset divided by the total number of n-grams. Inverse flash reading is, which grades text from 100 to 0, 100 indicating the most readable and 0 indicating difficult to read. A reciprocal of this measure is taken. And finally, n-gram and character diversity. Using the Shannon index and equitability, the authors calculate the diversity and equitability of n-grams and characters. The authors consider these various properties of each data characteristic and propose a 48-dimensional feature vector to represent the complexity of the given data. On the right side, you can see the different characteristics of the data and the properties within each characteristic. The number in the parenthesis denotes the number of dimensions assigned to each data characteristic. Once the 48-dimensional feature vector is constructed for each dataset, there are 2 to the power 48 possible combinations of metrics which can be designed from this feature representation. In order to intelligently traverse this search space and find the best metric, authors propose usage of genetic algorithms. These algorithms function based on a fitness function to rank a combination. In the current settings, authors use the Pearson correlation between the difficulty score obtained from a given combination and the accuracies of the different models obtained on this dataset. Stronger the negative correlation of the metric and the model accuracy, better is the metric. To identify the best metric, authors use a database consisting of 89 datasets and also consider 12 different models for each dataset. Based on the experiments, the authors showcase the best metric they identified to describe the data complexity. On the right, you can see the metric which has a strong negative correlation of minus 0.88 with the model accuracy. For a qualitative analysis, we can look at the provided plot. On the x-axis is the difficulty of a dataset measured using the given metric D2, and on the y-axis is the F1 score of the models. It can be observed from the plots that as we move from left to right on the x-axis, the model performances are dropping. For low data difficulty, model performances are high, but when we consider datasets with higher difficulty, we can see model performance getting poor, thereby illustrating the effectiveness of the identified metric. In this way, the authors have proposed a generic framework for capturing text classification dataset difficulty, which can be used as an analysis tool and a performance estimator to provide a measure of quality. We have now seen the different properties of text data that can be analyzed to measure its quality, and the different approaches that have been explored in prior art to address some of these. We will now take a quick look at the current state of affairs and the future directions in this domain. One of the important questions that is still an open research problem is how do we assess the overall text quality? Since problems to measure text data quality are so diverse, one possible solution is to design a framework that allows a user to assess the text quality across various dimensions. Another issue with the current approaches is the lack of standardized scores as output for each quality measure, which would serve consistent insights and provide useful indicators for low versus high score. Such a framework should also support specific recommendations for addressing poor text quality and evidence of model performance improvement for each text data quality metric. Although quality of text is necessary to determine the performance of the NLP models, a valid question to ask is how do we assess the quality of the different NLP models? This is the focus of the paper titled Beyond Accuracy, Behavioral Testing of NLP Models with Checklist by Ribeiro et al., which received the Best Paper Award at ACL this year. The authors specifically highlight the issues with the model generalization, such as held out datasets that are often not comprehensive. They contain the same biases as the training data. Real world performance may be overestimated, and difficult to figure out where model is failing and how to fix it. To this end, the authors propose a comprehensive behavioral testing framework called Checklist that is model agnostic and employs a task agnostic testing methodology that tests individual capabilities of the model using different test types. In future, combining a framework that systematically identifies the text data quality and a framework such as checklists to systematically capture the nuances of the NLP models would serve as a holy grail for an auto text pipeline for unstructured text data and NLP models. Thank you.